lesson is going to focus on addition and subtraction identities, and it is a two-part lesson. So this is the first part. To be successful at this lesson, we need to know what are the sum and difference identities that are outlined here. These are also listed within our these are also listed within your trig identity sheet that we have just off to the left-hand side underneath the basic identities. And these are super helpful, especially if we want to rewrite expressions in other forms or to rewrite an angle in terms of simpler angles that we do know the evaluation for. So when I look at, as an example, cosine of 75 degrees, it's asking for the exact value of cosine of 75 degrees. But 75 degrees is not on our unit circle. But what I can do is rewrite 75 degrees into two values that I do know the exact values for. So I could treat this as cosine of 75 degrees is the same as cosine of 30 degrees plus 45 degrees. So now I've rewritten it such that I've got the sum of two values within cosine. So I can utilize the sum and difference identity to expand it, utilizing terms that I do know. So I'm going to let 30 degrees be our alpha and then 45 degrees be beta. This is then the same thing as cosine of alpha, or 30 degrees, times cosine of beta of 45 degrees. Notice this is subtraction within the identity itself. Sine of alpha times sine of beta. And then we'll go ahead and evaluate them utilizing our unit circle. I know that cosine of 30 degrees is square root 3 over 2, and cosine of 45 degrees is square root 2 over 2, minus, I know sine of 30 degrees is half, and sine of 45 degrees is also square root 2 over 2. Now I can simplify. This gives us then square root 6 over 4 minus square root 2 over 4. And while I can't reduce square root 6 over 4 or square root 2 over 4, what I can do is write them as one fraction, thus square root 6 minus square root 2 all over 4, since they have that common denominator. We even can do this when we're talking about radians. So find the exact value of sine of pi over 12. So we might have to be a little creative here, thinking about the values that I know around the unit circle. So I also know that perhaps if I did 4 pi over 12 and I subtract 3 pi over 12, that gives us 1 pi over 12. But I also know that 4 pi over 12 reduces to pi over 3, and 3 pi over 12 reduces to pi over 4. So I can say that sine of pi over 12 then is the same as sine of pi over 3, minus pi over 4. And then using the difference of sine, so when we look at our bottom row, we're going to be using the difference of sine to rewrite. This then will provide us with sine of pi over 3 times cosine of pi over 4 minus cosine of pi over 3 times sine of pi over 4. And then let's evaluate what we can. Sine of pi over 3 is square roots 3 over 2, and cosine of pi over 4 is square root 2 over 2. Cosine of pi over 3 is half, And sine of pi over 4 is square root 2 over 2. We end up with square root 6 over 4 minus square roots 2 over 4. And just like our last one, we'll write it all over 4. Now it's giving us the difference of sine, and it's asking us to write it in terms of sine and cosine. So I can use the same rule I did in example 2, except I have x and pi over 4. So it'll look very similar to what we just did. This time though, I'll have sine of x, since that's our alpha, and beta is pi over 4 here, times cosine of pi over 4 minus cosine of x, our alpha, times sine of pi over 4. And where possible, we should always evaluate. I know that cosine of pi over 4 we said is square root 2 over 2. So I'll have square roots 2 over 2 times sine of x, because I'm not able to evaluate sine of x. And then I'll have the same here, because I know sine of pi over 4 is also square root 2 over 2. But this time times cosine of x. You certainly could factor if desired, if it asks you to do so, but it is already written in sine and cosine, and we are simplified. So at this point, I could say I'm finished. Here it's asking us to do a proof. And we're going to use a proof utilizing our sum and difference of sine. Typically, I'll always have us start with the left-hand side, or what looks like the more difficult side, and move our way to the simpler side. So I might want to consider starting with sine of a plus b over sine of a minus b using our sum or difference rules from the first page, and see what happens. This then gives us sine of a times cosine of b plus cosine of a times sine of b, all over the difference of sine. So sine of a times cosine of b minus cosine of a sine of b. But I don't want you to fall into the trap that you can start eliminating, right? Because we are attached with addition and subtraction here, so we are not allowed to just start eliminating common factors because we're not factored quite yet. And thus, don't fall into that trap. And there doesn't seem to be a lot that I can do here in order to reach tangent. So perhaps what I should do is actually start with the tangent side and rewrite our tangents as sine and cosines and see if anything comes up. See what we can find. So I know tangent of a is the same as sine of a over cosine of a plus sine of b over cosine of b. And this is all over, and I'll do the same in the denominator here, sine of a over cosine of a minus sine of b over cosine of b. Well, in each instance, what I'm going to do is eliminate those fractions. We only have one fraction from our step above, not a complex fraction. So I'm going to multiply my numerator by cosine of a times cosine of b, that common denominator. And notice that that is also the same as the denominator down below here. So I'm going to multiply this one by cosine of a times cosine of b. And by doing so, I am multiplying by a factor of 1, so I'm really not changing anything. So as I multiply this first one times our first term in the numerator, I'll notice my cosines of a are eliminated. So I'm left with sine of a times cosine of b plus, and I'll do the same here and here. And I notice this time my cosine of b's are eliminated. So I'm left with sine of b times cosine of a all over, and I'll do the same with our denominator of our complex fraction. Again, our cosine of a's are eliminated, so I'm left with sine of a times cosine of b minus sine of b. Here our cosines of b's are eliminated, so times cosine of a. This is very similar to our first step that we did, except here our cosines and sines are flip-flopped, but we know that we are able to rewrite them when multiplication. It doesn't matter the order in which we multiply. So our numerator is, in fact, if we go back here, our sum of sine, thus sine of a plus b. And in our denominator, it's the same thing, right? I can rewrite and flip-flop these two factors around in either case, because it doesn't matter the order in which we multiply, we'll still have the same value. And thus that gives us the difference of sign. So we have, in fact, in this case, we proved that the right-hand side is equal to the left-hand side by using the sum and difference identities. Here it's asking us to solve sine of x times sine of 2x plus cosine of x times cosine of 2x. So I have two sines being multiplied added to two cosines being multiplied. So when we go back to our original slide, looking at the opportunities that we might have, we have, of course, two sines being multiplied and then added to two cosines multiplied. And it appears as if we're going to be able to utilize the difference of cosines. Okay. The only difference is that these are flip-flopped in our problem, right? We could certainly rewrite them to match because we're in addition. In addition, we know it doesn't matter the order in which we add, we'll still arrive at the same result. So we can rewrite this then as cosine of, so our alpha and our beta here, so x minus 2x equals square root 3 over 2. Subtracting inside, since they have common terms, we'll have cosine of negative x is square root 3 over 2. Notice here we have an even or odd identity that we need to tackle. So with our negative angle identity or even odd identity from our identity sheet, I know this is the same thing as cosine of x is square root 3 over 2. So we're asking ourselves, where is cosine equal to square root 3 over 2? I know that it's equal to square root 3 over 2 in two locations. We have pi over 6 as well as 11 pi over 6 in the fourth quadrant. It doesn't ask us to identify all solutions or just a certain amount of solutions around the unit circle. So we can assume that we need to find all solutions. So we need all multiples of 2 pi for each one of these every time we go around that unit circle. Let's rewrite 4 times sine of 3x plus pi over 3 as a sum of sine and cosine. So it looks like I have the sum of sine here. So ideally, we've got our alpha and our beta. So this is the same as taking 4 times sine of 3x times cosine of pi over 3 plus cosine of 3x times sine of pi over 3. I can evaluate the cosine and sine of pi over 3. So I'll do that before I eliminate our parentheses or our brackets. I'll have sine of 3x, which we can't evaluate, but I know that cosine is half. And cosine of 3x times square root 3 over 2. Okay, so let's multiply by 4. So if I multiply 4 times half times sine of 3x, we'll have 2 times sine of 3x. And if I multiply 4 times square root 3 over 2 times cosine of 3x, we'll also have 2 square roots 3 times cosine of 3x. Nothing else that we can do here. I guess we could factor out the common factor of 2, but it is just as easy to leave this as is. Which leads us to the bottom portion, asking us to rewrite a sum of sine as a single sign. So starting from here, I want to rewrite it how we started. That would be our goal. So there are some things that we can notice within the portion down below. So it says to rewrite m times sine of bx. So notice how this first term pairs with the first term here. So 2 would be our m value, and our b value here would be 3x, plus n times cosine of bx. So here's another one. Here's our cosine version. Notice our b's are the same in both. And here is our n value. And then rewriting it as a times sine of bx plus c, we would need to find out what a is. So how do we get the 4 out front? Follows from taking Pythagorean's theorem that a squared is equal to m squared plus n squared. Once I find a, I can then evaluate at cosine and sine to find our a value. And you have to do both of them. So you can either use the last 2 equations to solve for possible values of c. Since there's always 2 possible solutions, we have to look at both of them to determine which quadrant c is in, which will help us determine which solution for c satisfies both. So let's see this in action on our next slide. I brought over the strategy that we're going to utilize, and it's asking us to rewrite 4 times square roots of 3 times sine of 2x minus 4 times cosine of 2x as a single sinusoidal function. So as a single sinusoidal function is asking us to rewrite it as a times sine of bx plus c. So then in the 4 times the square roots 3 times sine of 2x, we have our m value, our b value. We're going to need to use -4 as our n value because notice in the directions of it has to be positive. So in our case, our n is negative, and then b. Let's start off by first finding a so that we can look at cosine of c and sine of c to solve in that manner. So a squared is equal to 4 square roots 3 squared plus -4 squared. So 16 times 3 plus another 16 gives us 64. Thus, a has to be 8. Now we can solve for c. We'll start with cosine of c is equal to our m value over our newfound a value, which reduces to square roots 3 over 2. Thus, C would have to equal either pi over 6 or 11 pi over 6, where on the unit circle is cosine square root 3 over 2. We're not sure which one of these needs to be the solution, which is why we also need to find sine of C. Sine of C is n over a. Negative 4 over our a value is negative half. So where is sine negative half? Sine is negative half at 7 pi over 6 as well as 11 pi over 6. So notice that the value in which they're the same is the value we need for our C value. So now we have A, B, and C, so we can now write it as that single sinusoidal equation, giving us 8 times sine of 2x plus 11 pi over 6. Let's do one more of these. Here we have negative 3 square roots 2 times sine of 5x plus 3 square roots 2 times cosine of 5x. So we have our m value is negative 3 square roots 2. Our n value is 3 square roots 2. And our b value certainly matches with 5x. So let's first start by finding a. A squared is negative 3 square roots 2 squared plus 3 square roots 2 squared. Let's see, roll of 9 times 2 plus 9 times 2, or 36 when I take 18 plus 18. Thus A has to equal 6. All right, so let's now solve for C. We have got two options that we need to find, so let's do cosine of C is our m value over our newfound a value, which reduces to negative square roots 2 over 2. So where is cosine negative square roots 2 over 2? And it is at, C would have to be 3 pi over 4 or 5 pi over 4 around the unit circle. Where is sine of C then, which is our n value, 3 square roots 2 over 2 over 6, which reduces to square root 2 over 2. So now I'm looking for where is sine square roots 2 over 2, and this would be at pi over 4 or 3 pi over 4. I see they're the same at 3 pi over 4. So we have our A, our B, and our C. Thus 6 times sine of B, 5x, plus C, 3 pi over 4. And that is where we will end this particular lesson.